Hey guys, I'm Jace. I'm the lead for experiment number 3, the vapor compression, refrigeration, and heat pump experiment. So our objectives for the experiment are measure the coefficient of performance, the COP, of a heat pump, and construct a pressure enthalpy diagram of the refrigeration cycle. A little bit of background on heat pumps. Heat pumps are thermal engines, and the point of them is to move heat from a lower temperature space to a higher temperature space. Heat pumps can either be like refrigerators, where their purpose is to remove heat from a space, or they can be what typically called heat pumps. The purpose is to maintain heated space. Either way, you're moving heat from a lower temperature source to a higher temperature source. It's just the purpose of the heat pump is reversed, whether it's a refrigerator or a heat pump. The coefficient of performance is a performance parameter of heat pumps. The COP is defined as your desired output over your required input. In our case, it's for a refrigerator system, it's the cooling effect divided by the work input. It's this ratio. For a heat pump, obviously our desired output is the heating effect over the work input. So in this case, it's the heat added over the work in. And this formula right here, it's since a heat pump and a refrigerator are kind of the same system, you can run one in reverse. So depending on the application, the coefficient of performance of if it's operating as a refrigerator is related to the coefficient of performance if it's operating a heat pump, and it's given in this equation right here. This is the ideal vapor compression refrigeration cycle. Between points 1 and point 2 going through the compressor, we have isentropic compression in a compressor. Then from point 2 to point 3, the compressed gas goes through the condenser and it ejects heat into the atmosphere. This is denoted as constant pressure heat rejection in a condenser. Then from point 3 to point 4, we have throttling and an expansion device. This takes the as the gas goes to the condenser, it cools into a liquid, and then it goes through the expansion valve and expands back into a gas again. Then from 4 to 1, we have constant pressure heat absorption in an evaporator. This rapidly expanded gas becomes very cold and absorbs heat from the cold refrigerated space, and then the cycle repeats. This is a pressure volume graph of the refrigeration cycle. Of note is that you can see from 2 to 3, there is constant pressure compression, and between stages 4 to 1, there's constant pressure expansion. And then on a temperature entropy diagram, you can observe that between 1 and 2, it's isentropic heat addition. And from 3 to 4, it's isentropic heat rejection. And I have the COP in terms of, for the ideal case, you can write the COP as ratio of the high temperature space or in terms of the high temperature space to the low temperature space. And that only works for the ideal case. Then on a pressure enthalpy diagram, you can see between 3 and 4, you can easily see that 3 and 4 is characterized by isenthalpic compression, and stages 1 and 2 is characterized by a pressure and enthalpy increase. And then when you're looking at a pressure enthalpy diagram, you can find the COP for refrigeration and heat pump system by taking the enthalpies of different stages and making a ratio of those. In a real cycle, we call the ideal refrigeration heat pump cycle the Carnot cycle, but in real life we can never get the Carnot cycle, we can only approach it. So Carnot cycles 2 reversible isothermal and 2 reversible isentropic processes, but in real processes, losses are induced by refrigerant leaves the evaporator superheated. So in a Carnot cycle, you just, on the TS diagram, you just barely make it to the saturation curve for best efficiency, but in real life they superheat the gas a little bit before it gets there so that you don't have any liquid going through the compressor, which is dangerous to the compressor. Also, there's a pressure drop and heat gain between the evaporator and condenser because of pipe losses, and there's conduction in the pipe and things like that. And entropy is generated in the expansion and throttling process, and during any heat exchange over finite temperature difference because of the second law of thermodynamics. This is our experimental apparatus. There's a lot going on here, but most importantly, anything labeled ST is a temperature sensor, anything labeled SP is a pressure sensor, The label SC is a flow sensor, and M's are manometers. And the apex right here is that's the throttling device, the expansion valve. The TXV is interesting because it is a closed system. It's a throttle device that controls flow rate of the coolant through the evaporator, and it can actually change the flow rate based on the temperature of the fluid leaving the condenser. So how it works is there's a sensing bulb on the other, I'm sorry, I said condenser, I meant evaporator. On the other side of the evaporator, there's a sensing bulb. It detects the temperature of the fluid leaving the evaporator. Usually this bulb is filled with some kind of fluid that expands or contracts. Usually sometimes it's the refrigerant fluid. And this pushes down on this diaphragm right here connected to this needle. There's a spring attached to the needle which pushes up constantly against the force from the sensing capillary, and there's a pressure equalization line that also pushes up. So the purpose of this is that if the coolant leaves the evaporator too warm, it's not refrigerating all the way through. It's not having heat expansion all the way through. So the diaphragm will open the valve a little bit and let more coolant flow through to reach a correct cooling rate, and it closes when the coolant is too cold. This is a example of COP calculation. We just took random values from somewhere, and you have to calculate the mass flow rate. Then you do an energy balance on the evaporator and on the outlet, and then you get the heat ejected from the evaporator, and then with your work in, you can calculate the COP from there. And we expect a COP between 1 and 5. That's typical. 5 is really good. 1 is useless. And our pH diagrams look similar to the ideal refrigeration cycle with differences because of real life laws. Okay, that's it.
All right, thank you, Jace.